Okay, thank you. Thank you for the introduction and also for inviting me. It's really good to be back here after such a long time. The topic I will tell you about is very down to earth. It's back from the Stone Ages. There is no ADS-CFT, there is no string theory. It's just QCD, plain old QCD as we know it. The surprising thing also for me is that there is still something new to say about this. And it's not only that lattice can calculate numbers more precisely and compare it to experiments, but the physical picture that we have about QCD also has some news. Okay, so just for a start, let's summarize what we are talking about. So, is there a pointer I can use, or
I thought there was a stick somewhere.
Yeah, I wasn't because of something. It doesn't. Oh, there's. Oh, there's the stick. Okay. Okay, so this is the partition function, and U is the gauge field, which, well, I'm a lattice person, so I think about it as a gauge field on the lattice, but you can think about it as a continuum gauge field as well. So we have a path integral, and this is the gauge action. And after integrating out the quarks, you get a quark determinant, which has the masses of the different quark flavors. Now we of course know that the U and the D quarks are almost massless. So for this reason, QCD has a large symmetry group, which is SU2 vector times SU2 axial times U1 vector times U1 axial. And the two interesting parts of this symmetry that I will be talking about is the U1A that is anomalous and also the SU2A that is spontaneously broken below the critical temperature. So these are approximate symmetries. Well, this one, this is not even approximate, because they would be exact symmetries if the quark masses were exactly zero. But compared to the QCD scale, the quark masses are very small. So it's a good approximation to talk about these symmetries. So first of all, let's talk about the SU2A symmetry. The order parameter is the chiral condensate, which is written in terms of the quark fields, psi bar psi, expectation of psi bar psi. So it's basically the quark propagator integrated out for all space-time. And you can easily write it in terms of the eigenvalues of the Dirac operator. If you use an eigenbasis, then this is essentially psi bar psi. Or if you use an integral notion, then using the fact that the spectrum is symmetric, you can put together the two eigenvalues occurring at symmetric points. And this is what you get for psi bar psi, because you have imaginary opposite sign pairs or zero eigenvalues. Okay, so the quantity that appears prominently in this formula is the spectral density of the Dirac operator times this expression that has a very interesting feature. But this expression means that the integral is dominated by the part of the spectrum, the eigenvalues that are smaller than the quark mass, roughly. So it cuts off the rest of the spectrum, and it concentrates the dominant part close to zero, smaller eigenvalues than the quark mass. And if you do some extreme thing and take the chiral limit, then the only thing that contributes is the spectral density at exactly zero. So this is what this factor does. And it is very important because this will play a prominent role in the rest, what I will be trying to do. And this is called the Banks-Kasher formula. Okay, just. So now the next thing that I would like to remind you of is that QCD has a finite temperature transition, which is actually in real life a crossover but there is a low temperature phase below the critical temperature where this SU2 chiral symmetry is broken, and the order parameter, the spectral density of the Dirac operator at 0 is non-zero. This signals the breaking of the symmetry, right? So this is just a schematic picture of the spectral density. This is the eigenvalue. The spectral density is symmetric around 0, and it has a non-zero value here. That means chiral symmetry is broken. Now, above the critical temperature, chiral symmetry is believed to be restored. So the order parameter is 0, and the spectral density looks roughly like this. And there is a scale here, which is something like roughly the lowest Matsubara frequency for the quarks. And of course, there is some, it is not cut off exactly at the Matsubara frequency because there is interaction. It's not free fermions, it's not free quarks, but they still interact with the gauge field. But the important thing is that there is nothing here. The spectral density is 0, and for free fermions, it would start at the Matsubara frequency. For interacting fermions, it goes a little bit below the Matsubara frequency, but the spectral density here is 0. So the important message from this is that the spectral density at 0 has to do with the realization of chiral symmetry, because that's the order parameter, chiral symmetry. This is what you would find if you read a textbook about high temperature QCD. So this is a traditional standard simple picture of spontaneous breaking and restoration of the SU2 axial symmetry. Now, the actual picture, if you look at lattice simulations, is a little bit different. And the difference is this spectral peak here, that you have this part of the spectrum, which behaves as I described to you one slide before, but then there is this spike appearing around 0. And this is something very strange. Well, I have to tell you that this is a lattice simulation in an approximation, and the determinant was not taken into account. It is called a quenched approximation when the quark back reaction is not taken into account, but I will talk about that later, and we will put that back. So don't worry, it will be the real, real QCD, not just this quenched approximation. Okay, so if you don't choose this, if you ignore this, then this is how the spectral density looks like.
Is there a simple argument why it's not a lattice artifact of finite size or some other?
Well, you can do simulations on different volumes, different lattice spacings, and it's still there. So the point is that to see this, it took some time for the lattice communities to see this, because to see this you need an action, a quark action that has good chiral symmetry, and that is not easy on the lattice. So a good chiral symmetric Dirac operator didn't come around came around only after some time, and even then it was very expensive. And dynamical simulations with the determinant are still not possible with the full determinant.
So if you neglect the determinant, are you taking like the mass of the quark to the determinant?
Yes, it's equivalent to that. It's something like that. Yes, because if you take the quark mass to infinity, then it doesn't matter.
So there is no axial.
Yes, it's somehow an artificial regime in some sense, but I will go back to QCD later on. So just bear with me, it will be repaired at some point. But what's very interesting is that if you look at lattice simulations without this, many of the physical properties are almost the same. It's very similar in some sense. So, okay, I don't want to go into that. So there is a story behind this. This is when chiral asymmetric lattice actions became available. And this is a very strong coupling, small volume, all sorts of things, simulation. And it was largely ignored for some time when these other people came around, and they also find this with better tools.
Which version of the lattice action?
Which version of the lattice
chiral symmetry?
It's the overlap action that we are talking about. That's the most people use that, and that has exact chiral symmetry. The other part is the so-called domain wall, which has a very good approximate chiral symmetry, but not exact chiral symmetry. Those are basically the two versions that lattice people use. And this figure was computed with the overlap action.
But for example, if you do the domain wall, it's still there, it's just smoothed out a little bit or destroys it completely?
Well, when you mean the domain wall, with the domain wall, there is a small residual mass in what they see. It's not exactly chiral symmetric, but almost.
Or it's kind of exponentially small.
Yeah, it's exponentially small. It's a 5-dimensional system, and the residual mass goes down exponentially in the extent in the 5th dimension. So that's very small, but not zero. With the overlap, it can be made 0 to machine precision.
Thomas was asking if the results are the same, but both ways of doing.
Oh, you mean with
the peak?
They find the peak also with, yes, I'm sorry, yes. Okay, so there are 3 questions I will ask and we'll try to answer. Why is there a spike at 0? This is something very dramatic because you don't expect anything happening way below the Matsubara frequency. That's something very special. So something must go on. The next thing that I will talk about is the suppression by the quark determinant. If you look at page up, if you look at this and imagine that I put the quark determinant back with light quarks, so the quark mass is very small, then this determinant will not like those lattice configurations which have these small eigenvalues. Because the small eigenvalues will suppress the determinant, the weight of those configurations will be suppressed, right? So you expect that if I put the determinant back in here, then this peak will go down or disappear or whatever. So in fact, some people were speculating that this is so-called quenched artifact because of the lack of the determinant. Okay, so this will be the second question, the suppression. How does the quark determinant suppress this peak? And the third question, how does the peak influence the realization of the chiral symmetry as the quark mass goes to 0? Because that's the important region for chiral symmetry. And in fact, what I will try to convince you of is that the Banks-Kesher formula is absolutely inapplicable in this case because this peak is actually singular. So you cannot just take the value of the spectral density at 0. But you can do something else. You can you can go back one step and look at the derivation again and take the right limits, and you can do it. Okay, so this is the story I want to tell you. This was the background, and this is the story I want to tell you. So the first thing I would like to convince you of is that the spectral peak is due to instantons. So let me just recapitulate for you what instantons are. Instantons are special gauge field configurations with sort of a topological winding. So you have somehow the gauge field covers the whole gauge group in a non-trivial, topological, non-trivial way. And in a simple way, you can just think about an instanton as a lump of action placed somewhere in space-time. And there are 2 types of these guys. There are positive and negative charge instantons and anti-instantons. And what is important for my story is that if you have an instanton or an anti-instanton, then the Dirac operator has an exact 0 eigenvalue. Right? This is something very non-trivial because in the Matsubara picture, the lowest eigenvalue for free fermions is at the lowest Matsubara mode. But if you put in an instanton, even at finite temperature, then you have an exact 0 eigenvalue. And this is protected by the so-called Zinger index theorem, that the eigenvalues are exactly 0. So in general, you can have many of these topological lumps, instantons and anti-instantons. If you have Ni instantons and Na anti-instantons, then the topological charge is the difference of the numbers. And it results in absolute value Q exact zero eigenvalues of the Dirac operator. The chirality depends on which one you have more of. And this is an important physical quantity, the fluctuation of the topological charge, the topological susceptibility. I will use this quantity later on. Okay, so all that you can learn from this is that there is a non-trivial way of putting eigenvalues to zero, way below the Matsubara frequency. So the question is, what happens if I put many instantons and anti-instantons into this system, which actually are there? We know from lattice simulations that instantons and anti-instantons are there. So just to understand what is going on, let's first look at the simplest non-trivial case where we have two instantons. If we have two instantons, that means the topological charge is 2, and we have two exact zero eigenvalues of the Dirac operator. What happens if there is an instanton and an anti-instanton? Just imagine that they are infinitely far away. Then they don't talk to each other. The eigenmodes are sitting on each object one zero eigenmode, one zero mode, one eigenmode with a zero eigenvalue. They don't talk to each other, so you have a positive and a negative chirality zero mode. But if you bring them closer together, they will mix and split in the usual way as you learned in quantum mechanics. So in this way, there are no exact zero eigenvalues, but there is a symmetric splitting of the two eigenvalues. They are still very close to zero. And the closer you bring the two objects together, the bigger the mixing will be and the bigger the splitting will be. Okay, so there is a way of making exact zero eigenvalues, and also there is a way of making eigenvalues that are in principle close to zero, especially close to zero if the mixing is small.
You're playing this kind of game with instanton and anti-instanton, can you do it also with fractional instantons?
In principle, you could do that, but that would be more complicated. Yes.
But is there any evidence that they show up?
Some people say so, but I'm not sure about that. Okay, so let's go back to reality instead of these artificial constructions of two instantons and an instanton and anti-instanton. Let's imagine there is an ensemble of these objects, many instantons and anti-instantons in a system in QCD above TC. So what happens to the instantons above TC? Finite temperature field theory, Euclidean field theory, works in a way that you squeeze the box in the temporal direction and write down the path integral, and that gives you finite temperature field theory. And if you squeeze the box in the temporal direction, then it means, very simply said, that the large instantons will be squeezed out of the system because they just don't fit into the small temporal direction. And the upshot is that there will be much fewer instantons. So there will be a very dilute gas of instantons and anti-instantons. They are typically far away from each other. And the other thing which we know at finite temperature is that the zero modes are exponentially localized as opposed to zero temperature where they are not exponentially, they fall as a power law. So exponentially localized zero modes dilute gas. So if you can imagine that the mixing of these near zero modes of instantons and anti-instantons will be small, because the eigenmodes are exponentially localized. So it's like the eigenmodes of, it's like the states of electrons on faraway atoms. There is not much mixing between them because they are far away and the wave functions are exponentially falling. So this means that if you have an ensemble of Ni instantons and anti-instantons, then what you have is this number Ni minus Ne absolute value exact zero modes. This is from the net topological charge. And the rest of the zero modes will split around zero, but split only a very little because the instantons, anti-instantons are far away. So these are the mixing near zero modes. And voila, you have the spectral peak. That's what I want to sell you. And this is just a conjecture at this point. I still have to convince you that the spectral peak is due to instantons and anti-instantons. Okay, so this is supposed to be the first step in convincing you of this. So suppose that if the instantons are far away from each other, then we can expect a free instanton gas. They don't talk to each other. There is no interaction among the instantons and anti-instantons. And if we have a free instanton gas, then the number of instantons and anti-instantons follows Poisson distributions, independent identical Poisson distributions. This is something you can easily derive. And the only parameter of this distribution is the topological susceptibility. The fluctuation, this measures the fluctuation of the topological charge. It's essentially the density of instantons and anti-instantons. This is the volume of the system. So if you want, this chi times V is the only parameter. This is the expectation of the number of instantons, the average number of instantons and anti-instantons. So this is how you expect the free instanton gas to behave. The probability of having different number of instantons and anti-instantons. And these two figures show you, from this you can easily deduce the distribution of the topological charge, which is just the difference of these two absolute value, and the distribution of the total number of objects, which is the sum of the two. And what I show here in the figure is a comparison of a lattice simulation data in red and the expectation from a free instanton gas in blue. And the only one that there's only one parameter to fit here is chi times V parameter of the distribution. And you can see that with a couple of orders of magnitude change, within a couple of orders of magnitude change where I have the data, there is a nice fit. So from this you can guess that the free instanton gas is a good description of these objects. And I will show you more evidence, of that. But before that, let me go back to putting back to determinant, because that is something I still have to do. So there are two things that we expect to change in this picture if you put back the determinant. That is with light dynamic quark. First of all, there is a suppression of small Dirac eigenvalues because the determinant is small if there are many small eigenvalues. So you will typically have fewer instantons if you reweight the configurations with this. And the second thing is that it is expected to introduce some interaction among instantons and anti-instantons. And that is very simple to understand. If you pull together an instanton and an anti-instanton, then the splitting around zero of the two eigenvalues will increase. So you have, in fact, larger eigenvalues. The closer the two objects are together, an instanton and an anti-instanton, the larger the two eigenvalues. So the determinant will want to pull them together to have larger eigenvalues instead of small eigenvalues when they are far away, right? So the question is, what happens to the spectral peak? And what happens to chiral symmetry if I put back the determinant and take the quark mass to zero? And for that, we need a Dirac operator with exact chiral symmetry, because we need the exact zero eigenvalues, and we have to resolve the peak in the spectral density, this spike. This is something that I told you already. And the problem is that lattice simulation with the determinant is presently not possible for two reasons. I mean, with the determinant, with the chiral Dirac operator, which is essentially the only one, is the overlap that is on the market. And there are two problems. One is that the overlap is about 100 times more expensive than a pedestrian old non-chiral Dirac operator. And the second problem is that it is very hard to describe when the configuration changes topology. Because when the topology changes, the determinant is discontinuous. And there are problems in the simulation, technical problems. Okay, so if it's not possible to directly attack this, then comes my idea that if you cannot simulate the whole system, just simulate the spike, because that's what you are interested in. And in fact, there is a very simple description, as I will show you, of just a spike. And simulating just a spike, looking at the spike, is much cheaper than anything else. So you can, in fact, do something. Okay, I will tell you later. So first, let me introduce the model of the spike. So this is what I will show you is a model of the Dirac operator in the subspace of zero modes. So first of all, we choose a good basis. A good basis, a basis of the zero modes of the individual instantons. And this is something that has been done already. It was done a long time ago by several people, and it went under the name of instanton liquid models or instanton gas models. There are two differences between what they did and what I am doing here. The first difference is that my model is much simpler than the old ones. And the second one is that, as I will show you, this model exactly describes the spectrum of the Dirac operator that you get on the lattice. So you are actually looking at the right thing here. But let me just introduce first the model. So first of all, you choose the number of instantons and anti-instantons from independent identical Poisson distributions with a certain parameter. Okay, so you decided these numbers, and then you place down the instantons and the anti-instantons in a three-dimensional box of some fixed size. Three-dimensional because the instantons, typically the instanton size is close to the size of the box in the temporal direction. So the temporal coordinate doesn't really matter. So you have Ni and Na of these objects randomly placed down in a box, in a cubic box of size L. And now you construct a matrix. And this will be the model of the Dirac operator in this basis of the zero modes. And this is just the Dirac operator in this subspace. And the way you do it is you have two diagonal blocks of zeros because zero modes of same type objects do not mix. They give you exact zero eigenvalues. And you have two almost identical off-diagonal blocks. And the matrix elements here will be this exponential type. As I told you that the eigenfunctions go down exponentially. And this is what you expect the exponent to be, basically the modular frequency. And there is one constant here, which I don't know, but this can be determined, and I will show you in the next slide. So this is the model. Just I will stop here just if anybody has any question, because it is very simple, but maybe I was very fast. So I can construct artificial configurations, gauge field configurations, by putting down instantons randomly, choosing the numbers randomly, putting them down randomly, and construct this model of the Dirac operator. It has the right chiral symmetry if you choose the gamma 5 to be +1 here, -1 here, which is the right choice because you know that the zero modes have plus and minus chirality. So it has all the right properties that you expect from the Dirac operator, but it is only the zero mode zone, the zero modes of the Dirac operator, and the near zero modes that are combined out of the exact zero modes. So this is the model, and this is a model for the quenched QCD without the determinant, because that is what I showed you to contain free instantons, and this is based on free instantons. Okay. So let's see now how can this parameter A determined. Of course, the instanton density can easily be computed by looking at how many zero eigenvalues I have on average, because that comes out of the simulation. You have an overlap Dirac operator, chiral Dirac operator, so you can just count the exact zero modes that are 0 to machine precision. And from that, you can reduce essentially the density of the instantons or the topological susceptibility. This is the parameter of the Poisson distribution. And the only parameter to be fitted is this prefactor in front of the exponential. And now you have several different possible choices. What I chose to do is I looked at the lowest eigenvalue of the Dirac operator on a set of configurations, lattice configurations, and the distribution of the lowest eigenvalue in a certain volume. And this is the distribution, the triangle. And then I can fit this parameter A, and you see that get a rather good fit. So that's already something that tells you that it might work actually, because it very nicely describes the distribution of the lowest eigenvalue, the details of the distribution. And now there is nothing more to fit. And the only thing you can do is check whether it actually works. And one way of checking it is to look at the distribution, for example, of the lowest eigenvalue, but in a different volume. In a larger volume, the lowest eigenvalue will be smaller typically, as you expect. And this is it. So this is the lattice distribution, the triangles, and this is no fit anymore because the parameter is already there. You already determined it from the other. And you can check several different things like the second lowest eigenvalue, the distribution of the second lowest eigenvalue, other volumes, restricting it to different topological charge sectors, everything. And it seems that everything fits. So it means that this very simple model describes the zero mode zone of the Dirac operator. So you have a model which is very simple, but it still works. Okay, but now let's go back to the task of putting back the determinant, because that's the non-trivial part. So on the lattice, you have an additional weight of each configuration, which is the determinant. I will use degenerate quarks and flavors of degenerate quarks for this small experiment, but you can, of course, generalize it. Now let's split the determinant into two pieces. This is the zero mode zone. So the product of the eigenvalues here times the rest, the bulk of the spectrum. And the thing is that the bulk, this part of the spectrum, is very weakly correlated to whatever happens here. So this part of the spectrum basically doesn't know about this part. And this means that if you are just interested in how the determinant will suppress this part, then you can just ignore this part because there is no correlation. It doesn't talk to that part. So let's approximate the determinant with only this zero mode zone part, this part, the product of the eigenvalues in the spike. And this can be consistently included in this random matrix model because all you have to do is take the original distribution that I showed you before, this is the quench, and reweight it with this factor. And you can easily simulate this. This is a simulation that you can do on a laptop. So it's not a big deal. It's not nearly a lattice simulation or anything. And the reason is that you have the dimension of the space you are working with is you have only a few dimensions, the number of zero modes. Okay, let's try to understand this. So this is the result of the simulation with the dynamical quarks, with the determinant put in, with NF equals 2 degenerate quarks. On the horizontal axis, there is a quark mass. So this is going into the chiral limit. And on the vertical axis, I plot a couple of different quantities. First of all, there is the topological susceptibility, and I divided it by the quench susceptibility, which was original model without the determinant, times m squared. And you see that this is almost 1, very close to 1. So you can conclude that this is proportional to m squared times chiral, almost equal. Similarly, the chiral condensate, I divide it by chiral times m, and you see that this is also like almost 1. So the chiral condensate is n times chi naught, basically, to a very good approximation. And This one, this guy that is not behaving nicely, this is the density of instantons. So taking the instantons and anti-instantons together, or just instantons. And this is of this form. So it has a constant, and there is a part that is proportional to m squared times kind of, because if you check this one. So if I divide it by this, then this is going to be singular because of this constant. Because I divided that. Okay, so that's the result of the simulation. So what now? Now let's try to understand it. What is going on actually? What do these instantons feel if you put in the determinant? What happens? This is the understanding, sort of. And what I would like to convince you of is that essentially you can understand everything in terms of a free instanton gas still, even though the quark determinant is expected to bring in some interactions. And the story goes like this. Let's assume for a moment that the eigenvalues, which are small in the spike, are much smaller than the quark. So the quark mass is somewhere away from the spike, larger value. Then the determinant is approximated by m to the ni plus na, because each instanton or anti-instanton will be the factor of n. These are small, these are much larger. So the determinant depends on the number of topological objects, not on their type or location, nothing. Depends on nothing. Now let's put in this approximation to the determinant. This is what comes from the Poisson distribution. So this factor times the determinant. So this is basically what the probability of the instanton number and anti-instanton number will be proportional to. And if I approximate the determinant with this, then something very nice happens. You can put this factor in here, and it will still be a Poisson distribution with this new density, right? M to the nf. So what happens is that the distribution of the number of instantons and anti-instantons is still Poisson, even though there is a determinant. So there is still a free instanton gas, but the susceptibility is suppressed by this factor. So it's proportional to M to the nf. This one. Okay? But the question is that I assume this, right? I assume that the eigenvalues are much smaller than the quark mass, and I'm taking the chiral limit, so I'm bringing the quark mass to 0. What is going on? Is this still true when I go with the quark mass to 0? How can this be true? And here is the answer. This is the quark determinant again, okay? And I pulled out this factor from the determinant. This factor and times the correction, and this is the correction when you actually have when the eigenvalues are not so small compared to the quark mass. So if the eigenvalues are small, the correction factor is just 1, and this is what you are interested in. What happens when you take the chiral? When you take the chiral limit, then the quark mass becomes smaller. This suppression factor will suppress the number of instantons, right? The instanton gas will become more dilute by this suppression factor. The matrix elements will be smaller because the instantons, anti-instantons will be farther away from each other. You remember it goes exponentially with the distance. So the matrix elements will be exponentially smaller as the gas becomes more dilute. And this will result in smaller eigenvalues. And the miracle is that the eigenvalues will always remain smaller than the quark mass because of this suppression, because the gas becomes more and more dilute, right? So even in the chiral limit, you have a free instanton gas. And this is why you have this behavior, even for very small quark masses. So I could stop the story here, but let's do another check just to make sure that it is really a free instanton gas. And the check is the following. I do two simulations in the model. One with a dynamical simulation with the determinant included, and one quenched without the determinant, but scaling down the topological susceptibility, the density of instantons, by n to the nf. And if my proposal in the previous slide is true, then the spectral densities should agree, right? Because that's what I told you. And these are the two spectral densities, and they nicely agree, but something happens here. What is this? This is the logarithm. So it's the density of the eigenvalues in the logarithm, just to zoom into the spectral peak. So there is something happening for the largest eigenvalues. There is some discrepancy. Actually, there are, if I zoomed into this part of the plot, and it's here. So in the dynamical case, there are more eigenvalues here. So there is, in fact, an excess of some instantons and anti-instantons that produce large eigenvalues. What are those? Those are pairs, instanton, anti-instanton pairs that are close together. At least that's what I expect. So in the dynamical case, I lied to you. It's not really a free instanton gas completely. There is some component of instanton, anti-instanton molecules that are produced by the determinant, as I told you like 20 minutes ago, because the determinant wants to pull together the pairs. And some more evidence of that is in this figure, where I do the exact same simulation, dynamical versus quenched, with a scaled down topological susceptibility. But now I plot the distance, the distribution of the distance of the nearest opposite charge objects. So I take an instanton and I find the nearest objects, record the distance, and this is the density of the distances. So you see, it's nice, nicely agrees, except for here at a very small distance. At very small distance, there is an excess of instantons and anti-instantons that are very close together. And
what sets the scale?
What sets the scale? The scale
Temperature
is,
or
yes, the temperature. Yes.
not the lattice scale?
No, it's the temperature. In fact, when you, for example, when you do quenched, then it's only the temperature that is available. So that there is nothing else. Actually, the critical temperature, that's the only scale. Okay, so there is some excess, and this actually will explain this. So instanton density doesn't go with the topological susceptibility. There is a constant term. This is what you would expect in the case of a free gas. And there is a constant term. There is a constant, in the chiral limit, there is a constant density of these molecules. But the nice thing about it is that the eigenvalues occur here. So they are not, they occur at a fixed point. They don't come closer to zero. So they will not contribute to the quantities that I'm interested in. And I will show you that in the, well, I think I will skip this because this is just to show you that the spectral density actually becomes singular in the infinite volume limit. I can discuss it if somebody is interested. But the important point is this. What happens if you want to apply the Banks casher? So let's try to compute the chiral condensate. So this is what I showed you in one of the first slides. And now I also told you that the eigenvalues in the spike have the property that they are much smaller than the quarks. They are always much smaller in the chiral. So if you use this approximation, then you can easily compute this, and each term just gives you a contribution of 1 over n, because this can be known. So you have to count how many terms you have. The terms you have is the number of zero nodes, the average number of actually the dimension of the matrix. So this goes like the density of instantons. So this is the average number of instantons in the free gas times the contribution of each term, and you can easily compute that. And that goes like m to the nf minus 1 times chi naught z. And this tells you that if nf is equal to 1, then this goes to a constant, which is non-zero, which would tell you that the symmetry is not restored because this is finite. But for one flavor, there is no symmetry, so there is no worry there. For two flavors, the symmetry is restored because this goes to 0. So if nf is 2, then this is proportional to the quark mass. And in fact, wait, I'm going in the wrong direction. And in fact, this is what we found, that is called proportional to the quark mass. So this is because nf is equals to 2, and this is m to the nf minus. So this explains the middle equation. Okay. So what about the U1 asymmetry? The U1 asymmetry and the restoration or non-restoration of the U1 asymmetry is the subject of a long debate in the lattice community. So there are two big collaborations. This is a Fritjof Karsh and company. So this is like US and German collaboration. This is the biggest Japanese collaboration. And they are using the largest supercomputers in the world to argue about this. And they use different types of quark discretizations. QCD uses staggered, GRQCD uses domain wall, and to some extent overlap, but it is sort of a cheating. I can tell you more about that if needed. And the quantity they are looking at is the difference of these susceptibilities. This is the pi, this is the delta meson susceptibility. So these are isovector and pseudoscalar and scalar. And the statement is that if this difference of the susceptibilities is non-zero, then the U1 asymmetry is not restored. And they are arguing whether it is 0 or non-zero. QCD says that it is non-zero, so the symmetry is not restored. GRQCD says otherwise, that it is 0. And there is a very simple way you can compute this in the model that I showed you, because this quantity can also be written in terms of the spectrum. I will not show you this, but you have to believe me. This is the way, if you write down the Dirac operator in terms of eigenmodes, then you can write this quantity in terms of the spectrum. And it is similar to psi bar psi, except that there is a square here and a square here. And in the same way, you can compute this quantity if lambda I are much smaller than the quark mass. And the result you get is that the result is proportional to n to the nf minus 2, which means that for two massless flavors, it is non-zero. So this is a result on a laptop and not on supercomputers. If you believe this model, then this is what you get. And there is a small contribution from the instanton and anti-instanton molecules, the m goes to 0 limit, but it is numerically small and goes to 0 limit. So, for example, it doesn't influence this result. Okay, so
I guess also your result on the previous slide already.
I'm sorry.
Your result on the previous slide was already consistent with that. Like just when you compute over psi bar psi, you saw that was proportional to an m to the power nf minus 1.
But that's different. I mean, that's
So, but if you believe that the U1 actually is restored, you should also believe that it's restored when an f is 1. So the theory with an f equals 1 also has an axial symmetry.
yes, that's right. Yes.
And that might also get restored at high temperature.
Yes, but if an f is 1, then that.
No, but on the previous slide that you just
Yeah,
psi bar psi, right?
Yes. You are right.
Psi bar psi is non-zero for.
Yeah. Right. Okay, so finally the conclusions. I think I'm on time, right? Good. So the conclusions at high temperature and non-interacting, we have non-interacting degrees of freedom in a strongly interacting theory, and you don't have to go to infinite temperature for that. All the story I told you is already valid just a bit above the critical temperature, where the instanton gas is dilute enough for this story to apply. So the 3 degrees of freedom are instantons and anti-instantons. There is a small side to the story for instanton, anti-instanton molecules, but they don't influence the chiral limit, the interesting quantities in the chiral limit. And the other interesting thing is, which I didn't exactly show you, but the Dirac spectral density has a singular peak at 0 at any finite temperature for any non-zero coordinates. And this is actually something similar that has been found in condensed matter systems as well. In condensed matter systems, you have a chiral symmetry when you have a bipartite lattice. And people were looking at Anderson localization in bipartite lattices with certain types of disorder. And there is a type of disorder which is completely analogous to QCD, and they found exactly this type of behavior. So that's very similar to this story. Now, chiral symmetry restoration is non-trivial in the sense that, for example, NF equals 2, for NF equals 2, the anomaly remains. And even though the axial SUNF part is restored, the order of the limits is essential. This is something strange that you don't expect. Normally, if a symmetry is restored, there is no spontaneous breaking of the symmetry, then no matter how you take the limits, you get 0. But here, in the case of the axial U1 symmetry, the order of the limits is actually important. You have to take first the infinite volume and then chiral limit. And this is the main result for QCD. And there are some nice papers by these people who obtained similar results, but only in a chiral expansion, but about n equals 0. Okay, I think that's all that I wanted to tell you.
Thank you. Any more comments or questions? See, sometimes simple models work.
Yeah.
Can I ask one more about this last line there? So are you saying that if we take, say, 3-flavor QCD, the general quarks,
in 3-flavor,
the U1 axial is restored?
No, actually, it doesn't necessarily go the other way around. So what is certainly true is that if it is non-zero, then it is broken. Symmetry
Right.
broken. That's clear.
Restored.
But the other way around, it's not necessarily true, because you might have some other operators that break the symmetry and have a non-zero expectation. So that's not trivial.
Okay.